Hello everyone, this is Dodd. Today I would like to talk about system design interview. We will design a video hosting site. Think this site like YouTube, Netflix, Vimeo, etc. So the problem statement is quite generic. It asks us to design a video hosting site. But what exactly is this video hosting site? Although the previous slide mentioned YouTube, Netflix, Vimeo, they still have different use cases. As an interviewee, it is our job to ask clarification here. Why? Because interviewer wants to see how we handle the ambiguity. This will show whether we can identify key pieces of the system and define a scope of the problem and understand how we approach system design, like in real life, and be clear on what functional pieces of the problem we will focus on. To do requirement clarification, there are some big categories that we can follow with. We can start with users and customers to identify functional requirements or system behavior, basically a bunch of API in our system that we'll provide. Then we can go with scale, read and write, performance, availability. All of them are non-functional requirements, which are the qualities of our system. Let's look at sample questions for users and customers. Who will use this system? In a video hosting site, we will have client generate video content and consume video content. Who will generate content? Is it user-generated content like YouTube does, or licensed content like Netflix does? For this interview, we assume the latter. We focus on licensed content. Then, who will consume the video content? It can be free public user like YouTube, or paid subscriber like Netflix. Here we focus on paid customer. Next question is how the system will be used. What are the main use cases? Here we focus on 4 use cases: search video, upload video, transcoding, and watch video. Now let's look at sample questions for scale. How many read queries per second? We assume 1 billion total users, and on average, one user views 5 videos per day. Our read query per second would be 1 times 10 power 9 times 5 divided by 24 hours times 3,600 seconds. The result is 57,000 read per second. How much data is required for read query per second? Let's assume the video content highest solution is FHD, which is full high definition. It is 1080 pixel image resolution, that is 1920 times 1080. This requires 5 megabits per second, so the outgoing bandwidth estimation will be 57,000 times 5 Mbps, which equals to 285 kmbps, which is 285 Gbps. How many write query per second? Assume we have 500 hours uploaded per month, and the video content format is still FHD with 5 Mbps. The incoming bandwidth estimation will be 500 times 3600 times 5 Mbps divided by 30 times 24 times 3600. The result is 3.47 Mbps. The storage estimation will be 500 times 3600 times 5 Mbps divided by 8 bit per byte. The result is 1,125,000 megabyte per month, which is 1.125 terabyte per month. Can there be spikes in traffic? We assume between 8 p.m. and 10 p.m. local time, traffic is 10 times of average traffic, so the read traffic will be 57K times 10 equals to 570K read per second. Sample questions for performance. What is expected write-to-read data delay? Since the raw video uploaded will be transcoded first, which might take up to hours to complete. What is expected P99 latency for read query? We assume it is 100 milliseconds. Sample questions for availability. What is expected availability? We assume 99% availability for search and watch function, which are public client-facing, and we assume 95% availability for upload and transcoding, which is internal use. Here is a step-by-step guidance on how to tackle the system design interview question. We will start with functional requirement, system API, and then non-functional requirements, system quality, and then high-level design, detailed design, and bottlenecks and trade-offs. Let's first look at functional requirement. For search video, we can define an API search video with single input parameter query, which is a string containing the search items. The return result is a JSON containing list of video resources, matching the search query. We can add pagination support with limit meaning maximum number of results returned in one request, and offset, which is page offset in the result set that should be returned. We can also add security support with access token, which is the API access token of a registered account. Then let's look at uploaded video. The input besides access token, we will have a video content parameter, which is a binary data of video to be uploaded. The return result is a JSON format of video resource. We also need to add metadata, which is the attributes of video, like title, description, tag, catalog, category, language, etc. For transcoding, we require video ID, origin format, and target format. Format contains the resolution and codec of video. For watch video, we will have a stream video with input parameter access token and video ID. We can improve this API to have offset and format. Offset is the time in seconds from the beginning of the video, and format is the requested codec and resolution for this video streaming. Let's look at non-functional requirements. Based on our previous clarification question, we will have average read query 57K read per second, and outgoing bandwidth 285 Gbps, and incoming bandwidth 3.47 Mbps, and storage estimate 1.125 TB per month. And the spike traffic between 8 p.m. and 10 p.m. is 570K read per second. How do we solve those challenges? For average read query, we can have load balancing, cache, to support high TPS. For large outgoing bandwidth, we can utilize Content Delivery Network (CDN). For incoming bandwidth, there is no concern here. For storage estimate, we can use distributed file system or object store. For spike traffic, we can use scheduled scaling. Let's now look at the performance part. Transcoding takes up to hours, and P99 latency for read queries are 100 milliseconds. This means transcoding is time-consuming, and most likely is a CPU-intensive job. We can use asynchronous processing with message queue to handle it. For latency, actually it can be split into response time plus delay. Response time is how long it costs server to process it. To reduce this time, we can use cache to store previous result. For delay, it is how long the request reach server from client network. For this part, we can deploy data centers in different regions to make server close to end users. Let's look at availability. 99% for public client facing and 95% for internal use. First, we need to have a way to measure availability. It requires our system to emit metrics, and based on those, we can set up alarms if certain metrics break our expected threshold. We will monitor our system and use dashboard to visually check system health periodically. For high availability, we can introduce redundancy from several aspects: hardware, software, data, and network. Each of them has lots of content that we will cover in the future videos. Then, let's look at high-level design. We can start with two questions. What data should we store, and how we store data? What data should we store? Our system will store uploaded raw video content and transcoded video content in different codec and resolution. Examples of codecs are H.264 and VP8. Resolutions can be 480p, 720p, and 1080p. Our system also needs to store video metadata. The schema of metadata can be video ID, title, description, tag, category, and language. For video content, we can introduce a video storage component. It can be distributed file system or object store. For video metadata, since it will be used for query search, we can store them in relational database or NoSQL database. For now, we just call it database component in our high-level design. Let's look at our high-level design diagram. From the left, we have public users and admin user. Public user will interact with our server for search and watch video. Admin user will upload video to server. Inside server, we will store video content in a separate video storage component and store video metadata in a metadata database. Our server can be split into web server and application server to better support the volume. Web server will focus on the HTTP, TCP connection request and response handling, and application server will focus on the business logic processing. And we will introduce another transcoding server to handle transcoding tasks, which are time-consuming. Application server will put tasks into processing queue. Transcoding server will fetch tasks from queue and process it. To handle large outgoing bandwidth, we will introduce CDN so that public user can stream video files from CDN instead of directly from our server. System design is an open-ended question, and we can go on and on for quite a long time. I know we haven't dived deep into detailed design and bottleneck and trade-off part. Those will be covered in the future video. Please comment below if you want to know more about those parts. And that's all the content for this video. If you like it, please give a thumb up. If you want to stay tuned, please subscribe to this channel. See you next time. Bye.